Yes, welcome back. We already started alternating current and electromagnetic radiations, chapter 21, and I believe you're already watching my channel. Subscribe it if not yet. For notification, press the bell button and share it. We finished up to resistors in AC circuit with example, and then capacitors in AC circuit with example. Now the next topic. What happens when we connect inductor with the alternating current source with the AC generator? You know what is inductor? Inductor, if you have a piece of wire, for example copper wire, and you make it spiral shape like this one, we call it inductor, right? So whenever current is flowing through any conductor, there is magnetic field around it, and these type of devices, they store magnetic field. I mean, they store energy in their magnetic field, and we can strengthen the magnetic field around the conductor if you have more and more number of turns. Right. So you might have seen some inductors in the lab, like these shapes and many others. Right. Different lengths and different number of turns. So, as I told you that this chapter, AC circuits, we are discussing the AC characteristics by considering two things. One, AC source, generator, and the second one, the element, component, like resistor and capacitor we finished. Now, inductor. So, we discussed already that resistance of ordinary resistor does not change with changing the frequency in the circuit. But capacitor, you have seen that its behavior changes with changing frequency, and that's the reason we don't call that resistance with the offered by the capacitor and inductor due to the reason that they have different behavior. Their resistance changes, so we call them reactance. So in case of capacitor, we discussed capacitive reactance, and here we will call this resistance inductive reactance. So inductive reactance is X sub L, L for inductor and X stands for the reactance. So of course this is a sort of resistance with the unit ohm. So the effective resistance of the coil or the inductor in the AC circuits is measured by a quantity called inductive reactance. This is the rule. Again, L is the inductance in the unit of Henry, capital H, and this is the frequency. Right, and in the unit of hertz, and this is the inductive reactance in the unit of ohms. Right. Similarly, actually we are interested to find out the voltage across the element which is connected with the AC source. Right now we have connected inductor with the AC source. So the voltage across inductor L RMS is equal to I multiplied by R resistance, which is Ohm's law. So as I told you, we are not calling it resistance, we are calling it reactance, inductive reactance. So this is the rule for that. Okay. Now to see whether they are in phase or lagging, one parameter is lagging from the other. You see here, voltage is here, right? It reaches, this is the current, and This is the voltage, right? You see, voltage is here and current reaches here. Okay, so the voltage across the inductor always leads the current by 90 degrees. So current is here, it leads voltage across inductor leads the current. So you see, right? This side leading and the other side, lagging behind. In capacitor, voltage was here down. Okay, we'll discuss it again once we go through RLC series circuit. Okay, this is how we decide, because it's really very important to decide. Okay, so again, if you look at the voltage, okay, this is the voltage. It starts from here. After one time period, it reaches here. Okay, and the current starts from here. It reaches after one time period here. So still it has to go up. So it takes 90 degree more traveling to reach that point, and in the meantime the voltage goes further 90 degrees. So this is how we decide their angle. Okay, so once we have voltage RMS, we can find out other values also, not a big deal. Let's go to solve related example. Yes. Alright. In purely inductive circuit, when you have inductor, we call it inductive circuit. Okay? If you have capacitor, we call it capacitor. So right now we have inductive. Purely inductor means we don't have any other element, only inductor. Okay, L is given to you, inductance, and V RMS is given to you. Find the inductive reactance and RMS current in the circuit if frequency is given to you this much. Right? Now, L is 25 milli. Milli means 10 raised to power minus 3 Henry. So this is your L. Okay? So first of all, XL. So it's, now if you increase frequency or inductance, reactance will be increasing, opposite to the capacitor. It was 1 divided by 2 pi FC. Alright, so first of all, let's calculate this much. 2 pi 60, 25. So you get XL in the unit of ohms, because it's a sort of resistance, 9.42. Yes. And now you have to calculate RMS current, right? So I and this one we just finished. Now we need that one. You see, again, we have Ohm's law. V is equal to I multiplied by R, and we need R in fact. So we need IRMS. I is equal to V over R. So instead of R, we are using XL. So V, how much? Yes, VRMS is given to you 1.50 10⁻², over XL 9.42. You would get 15.9 ampere. This is your Okay, finished. All right. Then, next topic. RLC series circuits. Series resonance circuit. Right. You see, before we connected resistor only, then we connected capacitor only, then we connected inductor. Now all together with the single AC source, AC generator, right? So this is the voltage across the resistor, this is the voltage across the inductor, and here we can measure the voltage across the capacitor. We can measure or we can calculate. And this is, by the way, experimental arrangement. I believe we have done it in the lab. This is your function generator. We can use any of the function by selecting the suitable knob, whether you need sawtooth function or square waveform or AC. So today we are discussing AC, so we focus on that. So this is the function generator. Okay, you can generate and use any type of function you need. This is the oscilloscope. As you see, you can monitor and you can measure different, the voltages, current, magnitude, their and time period, and we can compare the waveforms. Right? Okay. Sorry, only spelling was missing. Okay, oscilloscope, E was going down, I'm sorry. All right, so this is, you see, L, inductor. We have knobs and you can select any value from here, okay? Any range of values. This is C for capacitor set. This is the resistor set. Any type of values you need, you can set, and you can select the frequency, maximum frequency, the level you want to see and you want to give to the circuit, RLC circuit, and this is how it works. Right. We have already done, as I told you, that voltage across resistor is equal to, according to Ohm's law, right? According to Ohm's law, V is equal to I multiplied by R. Okay? I max multiplied by resistor in case of the resistor. Okay? And this is for inductor. We just finished inductor. I max multiplied by XL. And this is for capacitor. Alright? And we have seen, if this is the current, and we have seen first of all that the voltage across the resistor is in phase with the current. You see, it starts from here, reaches here. Same time, reaches its maximum value and 0 and minimum value. So, voltage across the resistor is in phase with the circuit current. Right? This is shown here also. I and voltage across the resistor in the same direction, in phase. Then inductor. We have seen that in case of inductor, we just finished before this topic, that voltage was leading. I do there, you can see in the previous slide. Okay, in the previous lecture, sorry, part 1. Now, this is current. Current, I'm showing along x-axis, okay? So this is voltage. Voltage is leading by current by 90 degree, and this is what you can see here. Okay, voltage is leading the current. So current start from here, and it is already on the top. So okay, right here. Start from here, it's here. So the current will reach later on. So voltage is leading. In case of capacitor, you see this is the current, and this is the voltage across the capacitor. So voltage is lagging behind. So this side. So this side is leading and this side is lagging. Leads mean it's going forward in this direction. Alright. Now, you see, now we are going to find out the resultant, like vector, you know, the voltage triangle and then the impedance triangle. You see, this is voltage across R. This is on the right side. This one here. Okay. Voltage across L up. Right? Voltage across capacitor down. Now, this is in one direction. No issues. This is along this direction, so I can find out like this one. Let me show it here. The voltage triangle. Okay. This is the same here, like vectors. This one is this, because this is only positive direction, minus this. Okay? Right? So this is leading. So this minus this, these two vectors are converted into single vector. This is on the positive direction, delta VL minus delta VC, this one. Now you can easily find out the resultant vector. This is one vector, this is second vector. From the first to the end, this is the resultant vector. In fact, we are using this vector, you know, the concept, but for this triangle. So we can find out, you see, this one here. I wrote it here. Okay? Pythagoras theorem, hypotenuse square is equal to base square plus perpendicular square. And then taking the square root, I would get this one. Now again, you see, this is equal to IR, right? And you see, this is equal to IR. R is Z, which is called the total resistance, we call impedance. I max, and I take common from here, right? Because V is equal to I max R. So it is square and then under root, so it comes here. I max square is common, so I bring it outside the square root, I max. Remaining this one, right? XL minus XC square. This goes with this, and Z, we call it the impedance is equal to this much only. Okay? Again, this is the total or the net resistance of R and C series circuit, but since it's the combination of a resistor whose behavior is constant, does not change with changing frequency, and L and C whose behavior change with changing frequency, we call them, their resistance are called reactance, inductive reactance and capacitive reactance. So total, again, we don't call it resistor because we have three components. We don't call it reactance because we have resistor also, another name, but again in the same units, ohm. So that is also in the units of ohm. Okay? Alright. So this is what I mean. If we use first voltage triangle, then this is impedance triangle, because we don't have current here cancelled. So we have instead of this is equal to I max multiplied by R, which is Z. Okay, here the same thing. Okay, I max resistor R. Here we have the same thing here also. So I max cancel, so we have only Z here R, and here we have XL minus XC. Okay? This one. So I cancel out, so we left with this one triangle and with this one. This is this one. Alright. And the phase angle, okay, phi, you see, tan theta is equal to perpendicular or base R. This is how we can calculate the phase angle. Now let's go to this example related with this RLC series set. Right. RLC AC circuit has resistance this, L inductance, capacitance, microfarad. So capacitance mean it's 3.50 times 10 raised to power minus 6 farad. Frequency is given and maximum voltage Vmax is given to you. Find the impedance of the circuit. First of all, A part of the question. Right? So impedance Z is, we just finished that R square XL minus XC square. Do you have XL and XC? No. You have to find out first XL and XC. You do have R. So first of all, we have to find out, XL, 2 pi FL, F60, L, where is L? Okay. So XL, you would get how much? 226 ohm. And XC, capacitance, 10 raised to power micro minus 6. So you would get finally 758 ohm. Now you can substitute these values easily. R, how much? 2.50 10 raised to power 2. XL, square, you would get that impedance 588. B part, you have to find out the maximum current in the circuit. So I max, you have to find out. Again, you have Ohm's law. So I is equal to voltage divided by resistor R. And keep in mind, we have three components. So total resistance is not R, it is Z, impedance. So voltage over Z, right? So we have 1.50, yes, Vmax, raised to 2 over Z, 588. So you would get 0.255 ampere Imax. Done. That was the B part. Now C part. C and D one by one. Yes, phase angle, first of all, tan inverse XL minus XC over R. Tan inverse R is given to you 2.50 and XL 226,758. You would get 64.8 with negative sign. Why? Because XC is greater than XL. When you have XC greater than that, mean the circuit is more capacitive. Than inductive. Okay? Right. If you have only capacitor, we say it is purely capacitive. Once you have more value for capacitive reactance than inductive, so we say it is more capacitive than inductive. See the difference, okay? And as I told you, negative sign means the circuit, yes, the current leads the applied voltage. Okay? This says leads the voltage. Okay? Once it is more capacitive. We have done it there. Right, number D part now. You have to find out the maximum voltage across the elements, all elements. You have three elements. So voltage across R, maximum voltage across then inductor L, maximum of course, and voltage across capacitor, maximum. According to Ohm's law, you see V is equal to I multiplied by R, so I max multiplied by R for the resistor, and I max is the same for all, but here we don't say R, we call it X sub L, here X sub C. I max, yes, how much we just finished in D part? 0.255. 0.255 is the current, and you have R given how much? Sorry, 2.5 times 10 raised to power 2. So you would get across resistor. Okay, and here you have XL. How much XL? 226 and 758. So here you would get, sorry, this is voltage, so this is V. Okay, and in case of inductor, you get voltage, and in case of capacitor, the maximum voltage across capacitor will be 193 volts. All right, and then it's resonance. How resonance occurs in RLC series circuit when you have connected all three components, you know, in series, RLC, connected with the AC source. Right. You see, we have done that. It's interesting. You know all these things: F frequency, C capacitance. Sorry, here L is the inductance, C capacitance, capacitive reactance, inductive reactance. And third one we have resistor, whose value does not change even when you change the frequency. It remains a constant. Its behavior is constant, linear. Right. Now, think of the large values. At larger values of frequency, 1 divided by larger, you will get smaller answer. Almost zero, not zero, but almost zero, very close to very close to zero once you are using kilohertz, right? And bigger value, this will be bigger. So at larger values, XL is very, very large as compared to X sub C. Means this will be dominating. XL is dominating. If you say this is too small, this will be 0, and you remember you have here impedance this one, okay? So it will be acting as inductive, and at smaller values of F, 1 by smaller, it will be larger. So XC dominates. It will be leading. Now at higher frequency, this will be dominating, and at smaller frequencies, XC will be dominating. It means there must be one frequency at which both XL and XC will be equal. That frequency is called resonance frequency. When XL is equal to XC, for example, if you have 20 and 20 minus 20, 0. So R square root R. So resistance impedance will be R. So it will be totally resistive circuit, right? And once you have a resistive circuit, at resonance frequency, once you have less and less resistance, which is the impedance, total resistance impedance, only depending on the R, this is 0. So the current will flow through the circuit very easily. So higher current at resonance frequency, right? Resonance frequency F sub R. This is F sub R, sorry. F sub R, resonance frequency. The current is maximum at resonance frequency, right? So for example, we can calculate the resonance frequency. This is 2 pi FL 1 upon 2 pi FC, right? And I need F on this side, so it will be F square 1 upon 4 pi square L and C. I come here. So this is resonance frequency. So if I take the square root, FR, resonance frequency will be equal to 1 upon 2 pi multiplied by C. Is the equation to find out the resonance frequency. You see, you have inductance L in Henry and capacitance C in Farad. So you can find out, you know, the resonance frequency, right? So RLC circuits are used to tune the frequencies of AM and FM, you know, the radios. So this is what you use there. Okay, so you resonate. So this is the graph as I have shown to you. Okay, thank you very much. I think that was the last topic. And you finished, please don't hesitate to communicate with me, to leave your comments. Any point you have confusion, do ask. I'll be happy to answer your question. Right, thank you very much, and see you in the next lecture, inshallah. Bye bye.